Welcome back. Thanks for joining me as we finish not only our look into entropy, but our look into the unit of chemical energetics more broadly. Well, today we're going to finish up by introducing a final concept called Gibbs free energy, delta G, and use the equation delta G equals delta H minus T delta S to determine the feasibility of a reaction. Entropy. We've been discussing entropy in a lot of depth, both at a conceptual level and also as of last lesson, we started introducing some numbers, some calculations you can do to arrive with figures and interpreting what those figures are telling us about our chemical reaction. We've said again and again, entropy is a measure of disorder where that is a favorable state. Increasing disorder is favorable. We said that the total entropy change doesn't only come from the system, so it doesn't only come from converting reactants into products and increasing the entropy, increasing the microstates or decreasing that way. It also comes from the enthalpy changes that occur. The fact that chemical reactions will give off or take in heat and energy from the surroundings. So we're going to affect the entropy of the surroundings as well. And to work out the total entropy change comes from both the entropy of the system and the entropy of the surroundings. We said that if we have a positive delta S, that means that entropy is increased. That's favorable. That means we have a feasible reaction or a spontaneous reaction. You can use them to mean the same thing. I very much have been. Conversely, if the entropy change is less than zero, that means we have a decrease in entropy. It's getting more ordered. That is unfavorable. That means the reaction is not feasible. And this idea of feasibility or spontaneity just means a reaction can happen, doesn't mean it will happen. So, what else have I got here? We've got that we know the delta S of the system, so we can calculate this. We can calculate the change in entropy of the system if we have the entropy of each of the products and we add them together. We get the sum of those, the sigma sign meaning the sum, and we subtract that from the sum of the entropy of the reactants, where those values are going to be given to you, and you can plug that in to work out the total entropy change of the system. And we can also get the entropy change of the surroundings by this equation, where it's equal to the minus delta H of the reaction. So the enthalpy change of the reaction, the energy change occurring there, divided by the temperature at standard conditions. This is going to be 298 Kelvin, and we pop a minus sign in front of it to get nice and consistent with our signs for enthalpy and what we know about entropy. So we have used those equations. We introduced those equations in the previous video. That's sitting there if you want a bit of consolidation or to go over that again. But what you might be thinking, what you might be starting to work out is that, well, we have an equation here and we have an equation there. I mean, why not combine these equations? If we know the delta S of the surroundings is that, why not pop that in there? And why not indeed? So why don't we head over here and have a look at what that looks like. So to start with, we said that the delta S, the total, is equal to the delta S of, I might make my S a bit more capital looking. I don't know if that made it any better. Delta S of the system plus the delta S of the surroundings. And we said that the delta S of the surroundings is equal to minus delta H over T. So if we've got that equal to that, and we've got that there, let's pop that in place of our delta S of the surroundings and see what we end up with. Well, what we end up with is delta S of the total is equal to the delta S of the system plus minus, well, plus and a minus using your mathematic rules, that makes a minus. So if you add a minus, you end up with minus delta H of the reaction. I'll be a bit more consistent with my plimsolls and my signs here. Delta H of the reaction divided by the temperature. Excellent. So this is very, very useful because what we've done is we've now, if I rewrite my delta S of the total here, we've now linked entropy changes and enthalpy changes all into one equation, which becomes super useful for reasons we'll explore in just a moment. Let's take this a step further. I'm going to multiply both sides of the equation by a negative t. by the negative temperature. Maths tells me that I'm allowed to do one thing to one side, do the same thing to the other side. We still end up with it equaling each other. And the reason why I'm doing this will make sense in a moment. So what do we have? We'll end up with minus T delta S of the total equaling minus T, and then we've got to multiply all of this by minus T, so the delta S of the system minus the delta H of the reaction over temperature. So we're going to multiply that by T, we're going to multiply that by T to end up with minus T delta S of the system. And then if we got T divided by T, they're going to cancel out, aren't they? So we're going to end up with, and then a minus times a minus, we're going to end up with plus the delta H of the reaction. So this is equal to minus T delta S of the total. So why did I do this? I did this because in thermodynamics, we have a term called Gibbs free energy, an important one that you might be able to have inferred from the title of this lesson is where I'm going with it. So what is Gibbs free energy? Well, that's a good question that we'll talk about in a minute. But for now, I'll just tell you that Gibbs free energy, where do I want to write this? I'll write this over here. Delta G, and again, we're at our standard conditions here. Our Gibbs free energy is equal to minus T delta S total, a total entropy change. What you might be able to see is that this is that. So we can plug and replace that one for our new term, which is delta G equals, and now I'm just going to flip them around. I'm just going to put them in different. So I'm going to bring the delta H, the reaction first, saying the same thing, just rewritten a bit differently. Minus T delta S of the system. We're ending up with this equation here. Let's do one final little thing. Well, we've got the delta H of the reaction and we got the delta S of the system. So what we're doing is we're just dealing with the chemical reaction at this point. The delta H, you could even say the delta H of the system, the delta S of the system, they're referring to the same thing, they're referring to the chemical reaction. So let's just simplify that a little bit more to end up with delta G, is it still on the screen? It is. Delta G is equal to delta H minus T delta S. And this here is the equation for Gibbs free energy. Oh, I'm trying to do a little box around it, I'm not succeeding. There we go. So this is the equation for what's called Gibbs free energy. Very, very useful. What we've done, why have we done this? Well, what we've done is we've gone from, looking at the total entropy change of both the system and the surroundings to then mathematically linking our entropy changes with our enthalpy changes. And then through that, we've just looked at the system. By introducing this idea of Gibbs, we're just now looking at our chemical reaction. So if we know the enthalpy change of the reaction, and if we know the entropy change of the reaction, which we can very much do, we can calculate this value for Gibbs free energy. And we'll talk about what that means momentarily. So here's everything written a little bit nicer. So we added our enthalpy term into our entropy equation. We multiplied both sides by minus T to end up with that. We then said that there's a term called Gibbs free energy. What does Gibbs free energy do? It's used to measure the amount of work a system can do. We're going to deep dive on that in just a second. But delta G can be defined as that, which we can plug in there. We end up with our overall equation for the Gibbs free energy, which is this one, which we're only dealing with the reaction of the system. Delta G is equal to delta H minus T delta S. They're all at standard conditions. We've got our plimsoll there. Very, very important equation. If nothing else sticks in the brain from this lesson, just paint that equation on the inside of your eyelids. Delta G equals delta H minus T delta S. Let's talk about what this Gibbs free energy means. Well, it was developed by an American scientist this time, Josiah Willard Gibbs, in the 1870s. And old mate Gibbs, he described it as the greatest amount of mechanical work which can be obtained from a given quantity of a certain substance in a given initial state. He then went on to detail some further parameters. What does this mean? Well, it's to do with the concept of work, which, if you're familiar with your physics, work can be defined mathematically, at least, as... I need some plimsolls there. Oh, what's going on up there? I got my things the wrong way around. Sorry, let's just fix this up. Delta S of the system. All right, so we can define work as force multiplied by distance, where when a force acts upon an object whilst it is moving, work is done on that object. So let's consider if we have a instance where I'm applying 100 newtons of force and I'm moving something, displacing it, say 2 meters. You could say I've done 200 joules of work in this situation, done something useful. I've moved it 2 meters. Let's say if I was applying 100 newtons on a different object, but I didn't displace it at all. Well, I haven't done any work. I've exerted force, but I haven't done any work. You know, let's say I've done a million newtons of force, but I haven't displaced it. I mean, a lot of force has been applied, but no work has been done. So work is a form of energy. We can see it's in joules there. But I like to think of work as being the energy needed to do something useful. So there needs to be a measure. There needs to be something that can be measured from the force that is being applied. Because as we saw over here, if it can't be measured, if there's no displacement, no distance, it's moving, we haven't done any work. Doesn't matter how much force has been applied. So Gibbs free energy is talking about the energy that is able in a chemical reaction to do work, that's able to do something useful, such as, drive a chemical reaction in whatever form that looks like. So Gibbs free energy can be thought of as the maximum amount of energy available to do work, to do something useful in our chemical reaction. And we can think of our equation as having two terms to help us wrap our heads around this a little bit more. We've got our free energy is going to be dependent on the enthalpy change, and it's going to be dependent on the entropy change, where the entropy change is linked to the temperature there. Let's think about this in another way. If I rewrite the equation that we had up here, I'm just going to ignore the plimsolls for the time being, just to make it nice and easy. So let's rearrange it to make delta H the total enthalpy change. Let's make the enthalpy change as the subject. We would end up with delta H is equal to delta G plus T delta S. Hopefully you agree with me there. So this is our enthalpy change. This is our overall, our total change in energy. So the total change in energy we have is determined by two things. So let's call that the total energy change. It's determined by this species here. Now this is energy, but this energy is not available to do anything useful. This is unavailable, not available, because it's all wrapped up in entropy. All that energy is wrapped up in all that entropy business, right? So this work is not available to do any work. Now, the energy that's not wrapped up in entropy, that's not wrapped up in disorder, is energy that's free, energy that's available. It's free energy. And if we have a sufficient amount of free energy, then, to go back to our definition, we can do work. we can do something useful. So the Gibbs free energy, just what it sounds like, free, available. It's energy that is there that can do something useful, that can do work, as opposed to the energy that's tied up in the entropy, that's not available to do work. So let's have a look here. Our Gibbs free energy is dependent. If we make our Gibbs free energy as the subject of the equation again, it's dependent on the enthalpy change. So is the energy being released to the surroundings? Is it exothermic, or is it taking energy in from the surroundings? Is it endothermic? And it's dependent on how the entropy is changing as well. Is the entropy, getting more disordered when we look at going from reactants to products, or is that getting more ordered, less disordered? So more disordered favorable, less disordered unfavorable. And we know that we've got all sorts of signs. We can have a negative enthalpy change, we can have a positive enthalpy change, we can obviously have a negative entropy change and a positive entropy change as well. Let's start plugging some numbers in. Delta G equals delta H minus T delta S has the units kilojoules per mole. Standard conditions, in order for a comparison to be fair, it needs to be standard conditions. So we got the classic pressure, temperature, and states that we're well familiar with by now. And what you might notice here is that we're back in kilojoules per mole, which is consistent with enthalpy, but our units for entropy was joules per Kelvin per mole. So we discussed in the previous video the idea that you've got to convert your entropy units. I mean, you could also convert your enthalpy units as long as they're consistent with one another in order to put them in the same equation. So we've now got a delta G, which is usually given in kilojoules per mole, a delta H, which is usually given in kilojoules per mole, but a delta S, which is given in joules per Kelvin per mole. So conversions need to be done in order to make them all consistent, to make them all congruent with one another. I know, why not just put them all as the same units, but this is where we're at, so we got to deal with it, and deal with it we shall. Let's try to understand what the sign of the Gibbs free energy is going to tell us. Well, it's going to tell us if a reaction is spontaneous or if a reaction is not spontaneous. And it's going to be determined, as we said, by our enthalpy change of the reaction and by our entropy change of our reaction. So let's consider an example where we know it's a spontaneous reaction. If I go back down here and if I rewrite the Gibbs free energy equation, delta G equals delta H minus T delta S. We discussed previously in terms of our system, if we have an increase in entropy, that's very much going to be favorable. Increasing entropies, increasing disorder, favorable. Then we talked about in terms of our surroundings, if we're giving heat off to the surroundings, that's also going to be favorable. That's going to increase the disorder and the entropy of the surroundings, which is favorable. So if we're giving off heat, we're going to end up with a negative sign there. So we know that if our delta H is exo, and we know that if our delta S is positive, we've got the conditions, very much got the conditions for a spontaneous reaction based on everything we've looked at in this entropy series. So what does this mean for our sign for delta G? So if this is going to give us a spontaneous reaction, if we have a negative delta H, and then we got a negative times a positive, we're going to end up with a negative, negative minus a negative. We're always going to end up with a negative delta G in a spontaneous reaction. So our value of delta G being negative means it's going to be spontaneous. And conversely, if our delta G is a positive value, and we'll talk about this a little bit more in just a moment as well, we're going to end up with a non-spontaneous reaction. Spontaneous reaction. Now again, you can use the word feasibility as well. I've just gone back to saying spontaneous, but feasible or non-feasible as well. Reaction is spontaneous if entropy increases, so a positive delta S value, and we know that exothermic reactions are likely to increase entropy as well, so if delta H is a negative value. Now we also know, what we didn't discuss, is that T is always a positive value because we're on the Kelvin. So we can't have a negative temperature because we're using kelvins, which are only positive values. Well, I mean, it could be 0, but it's not going to be negative is important. So if that's positive, that's positive. We got negative times by the positives there. We're going to end up with that negative. So just reiterating what we were saying over here. The sign of delta G will dictate if a reaction is spontaneous. So like we just said, delta G is less than 0. It's a negative number. The reaction is spontaneous or feasible. It can be referred to as an exergonic reaction, which is a new word that looks similar to what we've seen before. You know, the idea of exothermic, endothermic, ex exiting, endo entering, and then thermics referring to thermal temperature. These words, exergonic, and what you might be able to infer is common, is endogonic. Again, the X and the endo, those prefixes referring to exiting or entering. The suffix here, this gonic, ergonic, it comes from a Greek word, ergon, which means work. So it's coming back all to this idea of work, energy available, the energy that can do something useful. So greater than 0, a positive delta G, non-spontaneous, not feasible, it can be referred to as endogonic. And then if delta G is equal to 0, the reaction is at equilibrium. There is no observable change. Let's give it a red hot try, eh? Here's a question. We've got a new equation that we can have a play with now. Delta G equals delta H minus T delta S. I've given you a delta H. I've given you a bunch of entropy values. So you've got to calculate the entropy change, which we've looked at before. Just to remind you on that one, we get the entropy of the products, the sum of, minus the sum of the entropy of the reactants. So that will give you your entropy change there. We've got an enthalpy change, and we have a temperature. Oop, don't look at that. We have a temperature, which is 298 Kelvin. Why don't you plug it all in and see if you can get an answer, and we shall go through it now. All right, I'm gonna rewrite some things here. We have our delta G. Let's get our black pen. Delta G equals, that looks like delta 6. Try again, Connor. Delta G equals delta H minus T delta S, standard conditions, boom, like so. We got our chemical reaction. Carbon dioxide plus hydrogen gas goes to forming methanol, CH3OH, liquid, plus H2O, liquid. Nice, can fit it all in. Where do we start? We've got a delta H to the reaction. We've got a temperature of the reaction. What we don't have a delta S of the reaction. So let's begin with that. Let's get ourselves a delta S here. So it's going to be the sum of the products minus the sum of the reactants. We have our products here. So we have a value for methanol. 126.8. 126.8 plus our entropy of water. Liquid water is 69.9 plus 69.9. And then we're going to subtract that from the reactants. So we have carbon dioxide, 1 molar equivalent of carbon dioxide, 214.7. 214.7. And importantly, like we said last time, you've got to take into account the stoichiometry. So we've got 3 molar equivalents of hydrogen. So we've got to get that entropy of 1 hydrogen. Whoop, don't look at that. Oh, I guess you've already done it by now if you have looked at that. 130.7. So 3 times 130.7. And we're going to plug all of this into Old Faithful here, which gives us 126.8 plus 69.9 minus 214.7 plus 3 lots of 130.7 to get a entropy change of minus 410.1 joules per Kelvin per mole. Now, we've got to convert this because we got kilojoules per mole, we got kilojoules per mole, we have joules per Kelvin per mole. I mean, you could convert these to joules, but why don't we just do 1 step instead of 2 steps? Let's divide that by 1,000 to end up with a kilojoules per mole, which I don't have to plug this in my calculator, is minus 0.410 kilojoules per Kelvin per mole. Nice one. Now we've got our delta S. Now it's just a matter of plugging and playing the rest of it in there. So let's go down. I'll get a different color to make it a bit more presentable. That's not a different color, that's the same color. So now let's go, our delta G is equal to delta H minus T delta S. We have a value for the enthalpy change, which was given to us, is minus 131, minus 131. We're gonna minus the temperature, which is 298, we're at standard conditions, and then we've calculated a entropy change. Once again, back to our old friend. Gonna plug all that in. Minus 131, minus 298 times minus 0.410, that gives us a value, that gives us a delta G, Gibbs free energy of minus 8.79 kilojoules per mole, like that. Which hopefully, if we come over here, we have a look at our value there. That is indeed what we have, minus 8.79 kilojoules per mole. We got a number. Numbers are useless if we don't know what the number's telling us. What is this telling us? We have a negative sign for our delta G. This is telling us that we have a spontaneous reaction. So this is telling us that from the total amount of energy available, there is 8.79 kilojoules per mole available, that's free to do work. Yeah, that's free to drive our chemical reaction or do whatever our chemical reaction is doing. Nice one. Let's talk more about these values, these signs for delta G, and the concept of entropy-driven reactions and enthalpy-driven reactions. Because enthalpy and entropy can either be working on the same team, we can think of it as, or working against each other. We talked about our example up here, where if they're both working together, you know, the delta H is negative, so we're creating more disorder. Our delta S is positive, so we're creating more disorder. They're on the same team. We're obviously going to end up with a spontaneous reaction. But we can have different combinations. We can have both negative, both positive, one negative, one positive, and that's going to determine what our spontaneity is going to be. So let's begin by looking at the one that we've already looked at. We have an exothermic reaction, so a negative delta H, with more disordered products. We have a positive delta S. Our first term is negative. Our second term, minus T plus delta S. Remember, our T is always positive, so we don't really have to consider that too much. Our T is always positive because it's a Kelvin scale. This is always going to give us a negative value for reasons we've already talked about, so let's not spend too much time on that. But essentially what this is saying is that if we have an exothermic reaction that creates more disordered products, our reaction will always be spontaneous. It doesn't matter what the value of temperature will be, that's always going to be a spontaneous reaction. Let's consider the complete inverse of that. We have an endothermic reaction, positive delta H, and we're having less disordered products. So just thinking about this logically, we can think the idea that we're decreasing disorder in our chemical reaction. We're creating more ordered products, which isn't favorable, and we're taking energy from the surroundings. So we're also making the surroundings more ordered. Both of these things are unfavorable things to do. We can think about this mathematically as well. We have a positive value here for our delta H. We have a negative value for our delta S. So negative times a negative, that's going to be a positive, right? You have a positive number and you add another positive number to that. Doesn't matter what those numbers are, you're always going to end up with an overall, a positive value. So endothermic reactions that have less disordered products always give a positive value. So these reactions will always be non-spontaneous for all values of temperature. Doesn't matter what you change that number to, because our temperature can only be positive, we're always going to end up with a positive delta G. Now, the other two are interesting because the other two can be altered by the temperature, because in these two instances that are left over, the entropy and the enthalpy of the reaction have different goals if we can personify them like that. Let's begin with which one? Let's begin with a exothermic reaction that is creating less disordered products. I'm going to go back over here. We're going to go on our page. So let's say that if we got delta G equals delta H minus T delta S, we've said that we have an exothermic reaction. So we have a negative value here, and we're creating a less disordered products. So we have a negative value there. So this is saying that our reaction is not increasing entropy, but our enthalpy change is increasing entropy. So they're working counterproductively, maybe is a word to use. So essentially, this is a minus times a minus, right? Minus times a minus gives a positive. So we end up with a negative number, and we're adding something to that. Now, delta G can end up being negative, or it can end up being positive. It's dependent on how big our positive number here is. So for example, let's just get a real simple idea. Let's say we have a minus 9, and let's say this T delta S ends up as plus 3. Well, that's obviously going to be a negative number overall. But let's say that this wasn't plus 3, let's say this was plus 10. Well, that's going to end up with a positive number overall. Now, how are we changing the size of this positive? Well, we're changing the temperature. If we have a lower temperature, 298 compared to 498, temperature is very much something that we can change. So this reaction here is going to be dependent on temperature. Well, the spontaneity, I should say, more accurately. However, the thing that is dictating if it's going to be spontaneous is the value of the enthalpy. This has to be a large enough negative number in order for it to be a spontaneous reaction. So if this is going to be a spontaneous reaction, this is going to be driven, it's going to be determined by the enthalpy of that reaction. So we could say that this is an enthalpy driven example here. Let me get a little line underneath. Look at that. So enthalpy driven, if we have a large enough negative delta H that it can overcome the negative delta S, we can end up with a spontaneous reaction. So the delta G will only be spontaneous if the delta H is more negative than minus T delta S, where the size of the second term will determine the spontaneity. We want to keep that second term, we want to keep the magnitude of that second term small. So we want the delta H to be larger, well, more exothermic than this is. We need that magnitude to be larger than this is. Maybe if I can be a bit more accurate saying that. So reaction is going to be spontaneous when the temperature is low, because we need the magnitude of the enthalpy change, the magnitude of the delta H to be larger than the magnitude of the T delta S. Hopefully you're still following me here. If not, I'm sure it'll come into fruition when we look at the converse of that. Now let's look at an endothermic reaction where we have more disordered products. Now in this instance, our reaction, our enthalpy change is not favorable, because our enthalpy change is decreasing the temperature of the surroundings, it's making it more ordered. However, our reaction itself is increasing disorder because we have a positive delta S, so we're making more disordered products. So they're working counterintuitively to each other again, but in the inverse to what we saw over here. So let's consider this over here. Now we have a delta G equals delta H minus T delta S, but we've got a positive value for our delta H, and we've got a positive value for our T delta S, where our minus times that positive over here is going to make this the negative value, and this is the positive value. So let's simplify this again. Let's say we have a delta H of 4, but we have the T delta S comes up to -9. Well, we're going to end up with a overall spontaneous reaction if that second term is larger. But if that second term, the magnitude of that second term is smaller, then we're going to end up with a non-spontaneous. So again, we can change the value of this T delta S because we can change the temperature. Now the negative part is coming from the entropy term. So if our delta G is going to end up negative, it means that our entropy change has to be big enough. We have to have a entropy driven as opposed to the enthalpy driven. It's an entropy driven because that's the term that's going to make it negative. So we have the inverse situation there. What have we written down here? The first term is positive. The second term will give a negative value. So the size of the second term is going to determine the spontaneity. Now this is the opposite. We've got to make this magnitude, we've got to make the magnitude of the second term larger than the magnitude of the first term. And we do that by increasing temperature. So in this instance, the entropy driven reactions will be spontaneous at high temperatures. Finish up today. Let's just look at some final ideas around Gibbs free energy. We can look at the Gibbs free energy of formation, very analogous to what we've seen with the enthalpy change of formation, just talking in terms of Gibbs free energy. The Gibbs free energy change when 1 mole of a substance in its standard state is formed from its element under standard conditions. Similar to enthalpy change, Gibbs free energy change of formation for an element is 0. So you can look at the free energy change when you're forming a compound, and usefully this tells us how stable a compound is, because the more negative, the more stable it is. So for example, we can think of this going in that direction as being very, very spontaneous because we have a negative value, we have a large negative value. But if we think about it going in the other direction, well, it's going to be the same size, just the opposite sign. So in this backwards direction, it's going to be very, very non-spontaneous. And the larger it is negative in the forward direction, the more stable it's going to be, and the vice versa of that. So we can do something very similar that we've seen with enthalpy changes to work out a Gibbs free energy of a reaction. We've talked about it as a measure of spontaneity or feasibility. We can determine it via an energy cycle. Only instead of using enthalpy changes, now we're using Gibbs free energy changes. But all based on the same principles there, that the energy is conserved. So we've got our direct routes. If we've got the delta G's of formations, and we've got the indirect routes, and we can do these energy cycles just the exact same way that we've done it with our delta H's, we can do it with our delta G's to determine the delta G of reaction. So you find your indirect route, you find your direct route, and if we say that delta G2 going this way is equal to that plus that, we can rearrange that to get the delta G of the reaction. And if we know both these delta G of the formations to go from the elements to our reactants, delta G of formation that way, elements to the products, delta G of formation that way, we can use Hess's law to calculate delta G of reaction using the energy cycle. And that concludes our lesson on Gibbs free energy. What have we done? We state and use the Gibbs equation, delta G equals delta H minus T delta S. We performed calculations using it. We stated whether reaction or process will be feasible, spontaneous, feasible, same description, by using the sign of delta G. And we predict the effect of temperature change on the feasibility of a reaction given standard enthalpy and entropy changes. As always, tasks, if you want to pause to consolidate what we've looked at, 1 column at a time, starting from the bottom, moving your way up. Fabulous. And that concludes not only our exploration of entropy, but also our unit on chemical energetics. Look forward to seeing you next time when we start something new. Enjoy your day. See you later.